This is the exploration of thermal diode effects of nitinol-based shape memory alloys, a Phase 2 project developed by Team 26034 of the 2026 University of Arizona's Capstone Engineering Senior Design Program. Has your laptop's fan ever started to sound like an aircraft engine when working and it feels like it's gonna blow up? Or perhaps, has your missile ever fallen short of its target due to the electronics malfunctioning during flight? Well, electronics tend to fail under really high temperatures due to overheating. In this project, we explored an alternative way to encapsulate electronics in advanced aerospace systems to better protect them from overheating. How? By further developing a nitinol-based thermal diode configuration to replace current electronic housing methods. Introducing our team: Connor Pasonikar, Integration Lead; Justin Nguyen, Procurement Lead; Liam Ellersick, Research and Analysis Lead; Alberto Leon, Documentation Lead; Zach Anderson, Verification Lead; Matias Contreras, Team Lead.
Our project is the Phase 2 version of a 2025 Senior Design project. Our main objective is to use analytical modeling to redesign this experiment in order to assess the feasibility of implementing our results into real-world applications.
There are 3 key terms to understand our project: nitinol, thermal diode, and rectification ratio. Nitinol is a nickel-titanium alloy with temperature-dependent properties that make it a good candidate for a thermal diode. A thermal diode is a device which allows heat to flow preferentially in one direction, which helps our mission of protecting electronics from the heat that they're exposed to. Finally, the rectification ratio is the relationship between the heat flow in the forward direction versus the heat flow in the reverse direction across the diode. This is what we use to measure the performance of our diode.
Our team's main objectives were to develop a test rig setup to evaluate the performance of a nitinol-based thermal diode and assess the feasibility of implementing a nitinol-based multilayer skin into advanced aerospace applications to better protect interior electronics from overheating. Additionally, other goals were to improve last year's study by designing a multi-layer aluminum thermal diode, testing for both transient and steady-state conditions, reducing heat leakage in the test rig, better enforcing one-dimensional heat flow to improve data accuracy, and implementing anti-aliasing measures for data collection. Other tasks also included building a mass equivalent and a volume equivalent control diode to compare data and create a comprehensive model from the data. This allowed us to analyze potential changes to the geometry of the diode. Let's go take a look at it.
To talk a little bit about how we approached the problem, we chose a multi-layer configuration for our diode as it was suggested by Dr. Francis Conis in his paper, suggesting that the best way to leverage the inherent properties of a shape memory alloy was to have increased layers as it increased the temperature range that the phase transition occurred over. Trade studies and thermal simulations were performed to determine the material selection and overall configuration of the thermal diode. While the phenomena that we're utilizing is a transient one, the team determined that we would need to test in both transient and steady-state conditions as the diode will be operating in both environments, meaning that it is crucial for us to characterize the diode in both. The steady-state conditions will be maintained for extended durations, maybe during a missile's pre-launch and factory power-on, and it would test the capacity for heat coming from the electronics to escape the housing. The transient conditions will be maintained for short periods of time during a missile's free flight, and it would test the capacity for our diode to protect the electronics from the outside heat. One of the issues that phase 1 of this project had is that they struggled with creating one-dimensional heat flow, making it harder to characterize the true heat flow. Our team tackled that problem by implementing a copper buffer block to even out the isotherms created by the cold spot that the patch heater produced. Another issue that the team had was heat leakage out of the sides of the diode stack, which we alleviated by implementing ceramic wool and flat stock GART heaters, which had 2 heating zones, powered by patch heaters to create a thermal gradient that matches that of the diode. We utilized 2 control samples, a mass and a volume equivalent of 6061 aluminum, which are standard in most missile systems, so we can actively compare the effectiveness of our diode to industry standard material. Instead of using straight blocks, we used plates that are the same dimensions of those in our diode, also joined with thermal epoxy. We did this so we could reduce the impact that epoxy has in our data. Our system requirements were divided in categories such as electrical and power, physical, thermal and functional performance, and measurement and data acquisition requirements. The most important ones were that our system achieved a rectification ratio greater or equal than 2.5 with a variability of less than 10% across 4 test cycles, that the heat flow through our system was predominantly one-dimensional according to specified margins, that the rig was able to reach and exceed Nitinol's phase transformation range, as well as reach steady state below it, and that the data collection implemented anti-aliasing measures.
So inside our test rig, we have our copper buffer blocks and our nitinol aluminum diode. The bottom buffer block has a patch heater attached to it, with the main purpose of the buffer block being to eliminate the cold spot that is produced by the patch heater. The top buffer block, which is actually this one right here, is where we'll have our heat flux sensor, which is the gray spot here, surrounded by Kapton tape. This is used to eliminate any failures in our one-dimensional heat flow due to the resistivity of the heat flux sensor. This diode stack is then put into our system. This system is made out of 4 insulating fire bricks joined with thermal cement. On the inside, you'll see that we have ceramic wool, which will be around all sides, as well as our guard heaters. These guard heaters are used to limit heat leakage out of the sides and further reinforce our one-dimensional heat flow. You can see that we have thermocouples going through the rig as well, with 4 per side. These are used to determine the difference between our guard heaters and diode stack, and are used to determine if we need to push more power into the guard heaters or take away power. So these are our power supplies, and when we're talking about how to collect data, first we got to talk about how we power our rig. We use these power supplies for every single part of our system. These 2 right here are used for our guard heaters, with this one covering the top end of the guard heater and this with the lower. This creates 2 different heat zones so that we can, in combination with our thermocouples, match our temperature of the guard heaters to the diode in real time. Currently, we have our setup in the transient form, but this can be easily switched to steady state by switching this end cap over there for our heat sink right here and our fan setup.
This is how the data looks like after tests. From this, we are able to get final results. These are our deliverables. While we were able to achieve a rectification ratio greater than 2.5, our testing indicates that nitinol is not efficient enough for the cost to replace aluminum 6061. This is due to the fact that the manufacturing process is much more labor intensive than traditional aluminum manufacturing, and for the needs of our sponsor, an entirely new manufacturing process would have to be produced to create minimal improvements for their applications.
Some of the key lessons we learned were that there is never just one way to approach a design problem. While completing this project, we had to evaluate multiple approaches and make decisions based on feasibility, budget, and time constraints. We also ran into a variety of roadblocks, such as turbulence during copper casting and even a patch heater failure, which forced us to adapt quickly. These experiences showed us the importance of prototyping early and being resilient throughout the design process. We would like to thank our sponsor, mentor, and everyone else who supported us along the way.